Hello and welcome to this video. Now this video contains a brief review of the concept of the push forward of a vector from the tangent space of one manifold to that of another, as covered in the video prior to this one. It then looks at two examples of the application of this concept. So let's make a start. All right. Now, from the previous video, we had a differentiable map between two smooth manifolds M and N. So M and N, remember they were smooth, there were no discontinuities, and there were no sharp changes in the gradient at any point. All right. Now, we found that, so we have M and N, we have a differentiable map, F that maps points on M to points on N, so point P on M becomes the point F of P on N. Right, we found that vectors can be pushed forward from one tangent space to another. So we had a vector in this tangent space, the tangent space at the point P to the manifold M, so tangent space of the manifold M at the point P, and this map mapped these points to this tangent space, the tangent space to N at the point F of P under this map. Okay, so we went from P to F of P. All right, and the push forward we found was the Jacobian of the function evaluated at the point P multiplied by the vector concerned. And that was a map from the tangent space of M at the point P to the tangent space of N at the point F of P. And that could be written in more usual notation. More commonly used notation was F star P. That's the push forward at the point P of the vector V. Okay, was then the Jacobian of the map evaluated at the point P times the vector P. All right, so that's what we found. All right, so, but how did we get that? So let's have a start of that. I'll just get rid of that. So let's have a look at this. So we started in one dimension with F is a map from R to R, from the reals to the reals. And the idea was with f of x was at the point P, we wanted to find an approximation to f of x, a simple linear approximation to it, because as simple as we can get is first order linear. And that's what we wanted, a first order linear approximation to f of x, but only at a point, because such a linear approximation, I mean, this is a curved plot. F of x is highly curved. And a linear approximation is just going to be this straight line here. So, but at the point P here, and for small values around P, that is a very good approximation. Very, very good approximation. So P under this map becomes here on the vertical axis F of P. All right. And so around that point P, we have an extremely good approximation. As we move away from P, for instance, at X here, you can see the approximation is very poor indeed. All right. And then as we go further, continually, it's just nowhere near the function f of x. But just at P and around P for small values, very good approximation. And that is what is going to help us. So this straight line here, tangent to the curve at the point P. So the equation of straight line, if you remember from secondary school, was y minus y1 is m times x minus x1 in parentheses. M is the gradient or the slope, and x1, y1 is just a point on the line, on the straight line. So we could rearrange that, have y equals m of x minus x1 in parentheses plus y1, right? Where x1, x1 is the point P, and y1 is the point f of P. Remember, that's a particular point on the straight line. And y equals f of x, general y equals f of x, and m equals f dash, the derivative of f evaluated at the point A, to give us the slope. And we can write that then f dash of A as d, the derivative of f of A evaluated at the point A. So the derivative of f evaluated at the point A. So for around the point P, we can give a good approximation to f, the map, right, from R to R, as being d f of A times x minus p plus f of p. All right, just using this straight line equation. Okay, so that's in one dimension. So domain is one dimension, range is one dimension. How about we step this up now to 2 dimensions? Okay, so what we have then is consider f as a map from R2 to R2, where x is x1, x2. X1 could be x and x2 could be y. Just depends. I'm just going to stick with x1 and x2. They could be anything. And P, the point of interest, that key point, is in 2 dimensions now, is going to be P1 and P2. Okay, first coordinate P1, second coordinate P2. So for a function f of x is made up of these component functions, f1 of x, a function of x1 and x2, and f2 is a function of x1 and x2. The Jacobian matrix d f of p now is going to be more sophisticated than just a single value at a point P. So d f of p will be partial f1 of partial x1 evaluated at point P. Remember, because C in here, f is evaluated at P, and we want the derivative of f evaluated at the point P. Partial f1, partial x2 evaluated at P, and then the second component function, partial f2 of partial x1 evaluated at P, and partial of f2 of partial over partial x2 evaluated at the point P. Now, the first order approximation of f around the point is still f of x is approximately d f of p times x minus p plus f of p. But now f of x is going to be df of p in 2 dimensions will be this Jacobian here, times x minus p will be this vector here, x1 minus p1, x2 minus p2. Remember, refer back to the previous video, what we're talking about there. Okay, in this case, we're going to be talking about replacing this with a vector v, which will have components in each of the directions, and then plus f1 of p, f2 of p, the component functions evaluated at p. All right, so that is f of x, and f of x allows us to take a vector on M, as we saw in the last video, and produce the vector on the other manifold, N. All right, it's the map that connects the 2 manifolds. F is a map from the first manifold to the second manifold. All right, but we can only do that around given points, a specific point. All right, so that was what the first video was about. So a brief reminder of that. What I'm going to do now is, let's just carry this on. So the push forward of the vector x minus p belongs to the tangent space of the manifold M at the point P is the vector d f of p dot x minus p belongs to the tangent space to N at the point f of p. Remember, so we've got point P here, we've got this vector x minus p, and we want to push it forward to this tangent space. All right, what does it become over here? Okay, now f star p of x minus p, so that's the push forward of this vector at the point P, is a map from the first tangent space, the tangent space to manifold M at the point P, is mapped to the tangent space to N at the point f of p. All right, so at point P we have some given vector, whatever it is, x minus p in this case, as we saw in the last video, and on the tangent space to N at the point f of p, it becomes this vector here, d, the Jacobian of the function f evaluated at the point P, times the vector concerned. All right, and so f star p of the vector x minus p is d f of p times x minus p. All right, and that's how we push the vector on this tangent space to this one. All right, remember, under the map f maps M to N, we take the point P on M and it becomes the point f of p under the map f to here at N. All right, that's the map. All right, so that's what we did last video. What I'd like to do now for the rest of this video is just look at 2 examples. So example 1, the push forward in 3 dimensions of a nonlinear map. So F is a nonlinear map in this case. So let's consider the case where M is R3 and N is R3. The map F from R3 to R3 is given by f of x, y, z, is each of these component functions here. And we're just going to simplify that by calling them U, K, and W. So U equals x squared plus yz, K is y squared plus xz, W is z squared plus xy. All right. You'll see later on at the end of the problem, it's much more convenient to do that. Now we're going to take the point P because it's F can't be approximated over the entire function F. All right, can only really be effectively for a simple linear first order approximation, really only approximated at a point. Okay, so we take the point P is 1, 1, 1, belongs to R3, and a vector V, some vector for the sake of this example, there's no particular reason otherwise, of this, which is a unit in the x direction evaluated at this point, and a unit in the y direction evaluated at this point here. Then the push forward of V under F, okay, the push forward of the vector V, this one, under F becomes, well, step one is compute the Jacobian of F. So the Jacobian df of F is the matrix of all first partial derivatives of the components of F. So partial F1, partial X, partial F1, partial Y, partial F1, partial Z. See all these? Same with F2, second component function in here, F1 here, F2, F3. Okay, so partial F3 with respect to partial X, partial F3 with respect to partial Y, partial F3 with respect to partial Z. And when you do that, you get 2x. If you take the derivative partial F1 here with respect to X, you're going to have 2x, so that goes there. Partial F1 with respect to Y will give you Z, and the partial of F1 with respect to Z will just give you Y. And then similarly for the second component function and the third component function. So that's what we get. So that first step is to compute the Jacobian of F. Next step. Evaluate the Jacobian at the point P. So we're going to substitute 1 into all of those. So we end up with df evaluated at 1, 1, 1, gives us 2 along the diagonals and 1 everywhere else. That's step 2. Step 3, apply the push forward of the vector V. So here's our vector V again at the point 1, 1, 1 on manifold M. Okay, partial Y. So unit in the x direction, unit in the y direction. Now, what we're going to do, make our life simple for ourselves, is to represent V in coordinates in this form, 1, 1, 0. The push forward F star P of V at P equals 1, 1, 1 is computed by matrix multiplication. So F star of P, F star P of V, the vector V, is the Jacobian of F evaluated at point 1, 1, 1 times the vector V, and the vector V in this component form here is 1, 1, 0, 1 in the x, 1 in the y, 0 in the z. So we carry out this multiplication and we end up with 2 by 1 is 2, plus 1 by 1 is 3. Okay, similarly here, 1 by 1 is 1, plus 1 by 2 is 2. The 0 here multiplied cancels out that column there, those terms there. And for the bottom one, or for that column actually, and then for the bottom one, 1 by 1 is 1, plus 1 by 1 is 2, plus 0 times 2 is 0, so we get 2 down here. So our vector under the push forward, our vector V push forward, is 3, 3, 2. All right, so let's write that. Also, at that point, F of P, F of 1, 1, 1 is, when you evaluate, if you can go back and pause the video and check for yourself, you'll find it's 2, 2, 2. So the push forward of the vector F star P of V at F is 1, 1, 1 is F star P of V is 3 partial U evaluated at F of 1, 1, 1 plus 3 times partial K evaluated at the same point plus 2 partial W evaluated at F of 1, 1, 1 again. Okay, when we tidy all that up, we get F star P of V, the vector V, is 3 times in a unit vector in the u direction at the point 2, 2, 2. Remember how we got that? Plus 3 times the vector in the k direction, evaluate the same point 2, 2, 2 on the manifold n. Remember, okay, these are the map values of the map on the manifold n. They have these coordinate values, okay, on the manifold n. And then plus 2 in the w direction, evaluate the point 2, 2, 2 on the manifold n, right? And that's our vector. So we've taken the vector 1, 1 on m, and we pushed it forward to 3, 3, 2, right, on the manifold n. Next one, example 2, push forward from R2 to R3. Remember, the manifolds don't have to have the same dimension. So consider a map f from R2 to R3 defined by f of xy is e to the x cos y, e to the x sine y, these components x plus y, okay? That's F1, F2, F3, and we can call them alpha 1, alpha 2, alpha 3, just as we did up here, because that makes our life easier. It just looks nicer instead of having F1 here, F2 here, F3 there. All right, step 1, we compute the Jacobian of the matrix F. So our Jacobian now will be 2 by 3, okay? 3 rows, 2 columns. Okay, so we have partial f1, partial x, partial f1, partial y, partial f2, partial x, partial f2, partial y, partial f3, partial x, partial f3, partial y. And when we do that, so the partial of f1 with respect to x, well, the derivative of that with respect to x is just going to be e to the x, and then times cos y. Okay, the partial of f1 with respect to y, if we differentiate this with respect to y, this becomes minus sine y. So we have minus e to the x sine y. Let me just go partial f3, partial x. So partial f3, partial x will just give me 1. The y doesn't come into it. It's just a constant on the end there. And when we differentiate with respect, well, it's not even that. When we differentiate with respect to x, this just disappears. It's a constant, it just disappears under differentiation. Partial f3 on partial y, well, same thing, the x doesn't count, it disappears because the derivative of this with respect to y is 0. Derivative of y with respect to y here is 1, so we get the 1, 1 down the bottom. Okay, likewise for the middle row. Next step. Now, let's say we evaluate the Jacobian at point p equals 0, 0. So we're going to do this one on the manifold M at the point 0, 0. And when we substitute that in, if you want to check back to the previous, you'll find that we get 1, 0, 0, 1, and 1, 1. Next step, we apply the push forward to a vector v. This one here, I didn't nominate it earlier, just as I didn't nominate point P, but here's a vector we'll use just for sake demonstration purposes. So V is 1 unit in the x direction minus 1 unit in the y direction at the point 0, 0 on manifold M. Now, representing V in coordinates as 1, minus 1, 1 unit here and minus 1 unit here. Okay, the push forward f star P of V at P equals 0, 0 is computed by matrix multiplication. So f star P of V is the Jacobian of f evaluated at 0, 0, this point here on M, times now this vector here in this component form here, okay, is 1, minus 1. When we carry out the multiplication, we end up with, well, 1 by 1 is 1, because 0 by minus 1 is nothing, so we end up with 1. 1 by 0 is nothing, minus 1 by 1 is minus 1, and 1 by 1 is 1, okay, and minus 1 by 1 is minus 1, adding together we get 0, all right? Thus the push forward vector f star P of V at f0, 0 is equal to 1, I should have here minus 1. Oh no. Oh, 1, 0, 0, that's all right, is, my apologies, I just got a fright there, I thought I made an error, but f0, 0 is equal to 1, 0, 0. If you substitute that in, you'll find that. my fault, my apologies. So on, just going back here, on n, the tangent space occurs at the point 1, x is 1, y is 0, okay? It occurs at 1, 0, 0 on the manifold n, not x, sorry. It occurs at the point 1, 0, 0 on n, and the push forward vector f star p of v is 1 in the sigma 1 direction at f of 0, 0, minus 1 in the 1 unit in the sigma 2 direction at f 0, 0. So evaluating that, f 0, 0 we know gives us 1, 0, 0. So on the manifold n, f star p of v is 1 unit in the positive sigma direction at this point on n, minus 1 unit in the sigma 2 direction at this point, right, on the manifold n. So here's our push forward vector. All right. So, and this vector is clearly a very different vector to the one we started with on M. And that's the process there. I hope that's useful to everyone. I can return that now. I hope everybody found the video useful. Again, it might be worth, after listening to me, to run through the video again, but without any sound, and just read the notes that are there and see that it's clear to you. I hope that helps. I hope that example opens your eyes a bit more and helps you to see what's going on. And I think I might just make one more video after this and show 2 examples from general relativity of the use of this push forward of vectors from one tangent space to another. All right, thank you very much for watching. Please like the video and subscribe. And I hope to see you in future videos. Thank you, everyone. All right, bye.